Hello, everyone. Welcome back. Welcome to this lecture, which starts a series of 3 lectures on block ciphers. Remember, with the last lecture, we basically finished off stream ciphers, and now we are going to cover block ciphers. The topic is comparatively simple because we are not going to dive into any other block cipher than AES. The advanced encryption standard is basically the block cipher, pretty much the only one that is actually used these days. So the first of these 3 lectures is gonna look at the mathematical foundations that are going to be applied in the AES algorithm. Then we are going to talk about, in the second lecture, we're going to talk about AES itself, how it works. So the pure, unrefined AES, if you want, which transforms 128 bits into, of plain text into 128 bits ciphertext. So in the third lecture, we are going to see that AES as such cannot be used. And we are going to see and get to know several ways of using AES in different scenarios, which are called modes of operations. Okay, so in this class, in this lecture, we are going to talk a little bit about AES and give some motivation. And then we are introducing finite fields. And the 2 finite fields that we are going to get to know are prime fields and extension fields. So we are diving a little bit into field theory, just about enough to understand how the mechanics of AES work. Okay, not more. So we are not going to provide any proofs. So this is a 1 lecture about a topic that you can have a whole semester on. And we are not going to use any more time on that. It is enough for our purposes. So motivation. It's important to understand that AES is the only block cipher, and it's the most important cipher in the world. So it's a very stable cipher, a very safe cipher. And as I said, what you have is you have 128 bits of input, and this is being transformed by the cipher into 128 bits of output ciphertext. And we may choose from a number of key lengths, 3 key lengths. So for our purposes, we are not going to look into the other key lengths, but 128. So the interesting thing about AES is that the internal operations are all based on finite fields. Okay, that's the reason why we have that little bit of an excursion into finite fields. So let's talk about finite fields. In English, we call finite fields also Galois fields. Galois fields seem to be a more fancy term, and I suggest that we use that from here on. Okay, so if your girlfriend or your boyfriend asks you, what did you do in lecture today? You can proudly say, well, we talked about Galois fields. So Galois itself, it's the name of a guy, and this guy died at the age of 21 in a duel. So I really invite you, this is an extremely interesting guy, very compassionate, short-tempered, and he died brilliant, absolutely brilliant. He died at 21 in a duel, and I encourage you to read his story, on Wikipedia. you know, just search on Google for Galois, and I give you the link here so that you don't even need to search. Have a look, it's really interesting. Okay, so field theory has to do with abstract algebra. There are three big structures in abstract algebra, which are groups, and we kind of touched on that already when we talked about groups and rings. So we have rings and we have fields. Okay, so these structures follow a hierarchy, as you can see, as follows. So groups allow only two operations, or basically one and the inverse operation. So plus and minus. Remember that a group is a set of elements with one operation. Okay. So an important property is closeness. So when you apply that one operation to two operands, what you are going to have is a result that is within the group again. So this is closeness. So you always land within the group if you apply operations on operands. So associativity, that's relatively straightforward. So if you do A, operation B, operation C, and I just do donuts here for the operation, it doesn't matter whether you do it in that order or in that order. Pretty much what you're used to anyways when you, you know, look at addition, something that you're more familiar with. So identity means that there is an element which is the identity element. So for a group under addition, for instance, we may have the identity element 0. So if we do A plus 0, it's the same thing as 0 plus A, which is A. So this is a hallmark of identity. And here again, in this case, we have the identity element 0, or neutral element. Sometimes it's called neutral element as well. So this is identity. And then there is invertibility, which means that each group element has an inverse. So for groups under addition, for instance, the inverse is, you know, minus A, and that yields the neutral element, the identity element 0. So this is for addition, okay? Invertibility. So every element has an inverse, okay? So let's now look, or a short excursion into rings and reiterate what we said before. Remember that in rings, plus and minus was, you know, defined. That is not a big deal. Multiplication was defined as well. But division, or the inverse, was not always defined. And remember that it depended really on the number of elements. For, you know, an integer ring 5, all of the elements had multiplicative inverses. The reason for this is that the 5 is a prime number, and all the other elements from 0 up to 4 do not share a common factor other than 1. So the greatest common divisor was 1 for any element, and 5, for instance. So, but if we have a ring 6, for instance, 6 factors, 2 and 2 times 3, so the 2 and the 3 would fall out of the picture. They would not have multiplicative inverses, just because they, the numbers, and 4 not either. 4 is 2 times 2, so 6 and 4 shares a common factor other than 1. For fields, all 4 elements are, 4 operations are being defined. So we have plus, minus, we have times, and we have the inverse. So the invertibility property is fulfilled, okay, for fields. So we'll see that we have prime fields, and they're called prime fields for a reason. Like in an integer ring, ring 5, we can have a Galois field 5. And in that case, all of the inverses are being defined. And convince yourself, as long as we do have a prime, in that field, the cardinality of that field to be a prime, that means that all the other elements have an inverse. And this is how we pull the trick off that all the elements have an inverse, basically by limiting our existence of these fields to prime numbers. Okay, so that jumped already a little bit ahead of the definition of a field. So all elements of a field, they form a group under addition with the group operation plus and the neutral element 0. So we just discussed that. But fields also, except 0, are a group under multiplication. The group operation, of course, is the multiplication symbol. So I apologize in advance if I'm not really consistent with that multiplicative symbol, the symbol for multiplication. I apologize. So please, judge by the context. So the neutral element would be 1. Okay. So convince yourself, and that was already up in the last homework, that if we have an element and its inverse, if we multiply those modulo by, the prime number that those elements, the corresponding group that those elements belong to, it's 1. Okay, so when 2 group operations are mixed, the distributivity law applies. So that's something that you are familiar with again. Not a big deal. A times in brackets or parentheses B plus C is A times B plus A times C. So this is pretty straightforward, and that hasn't changed here. All of these operations, of course, are, and for our purposes, are going to be modulo operations. So let's give a few more common examples for fields. Real numbers are fields. This time not with modulo reduction. So if we have real numbers and we apply these operations, of course, the inverse exists in real numbers. If you have a number A, the inverse is 1 over A, and A times 1 over A is 1. So we have that neutral element 1. But convince yourself, if you have, 7 and 1 over 7 is also a member of the real numbers. So there's no contradiction. And, a similar train of thought applies for complex numbers. And that said, especially when it comes to groups under multiplication, you should convince yourself that the natural numbers and the integers are not fields. So because they are not groups under multiplication, and the reason is that the inverse of those guys are not in the group. So the closeness property is not fulfilled, because if you have a natural number 5, 1 over 5 as an inverse is not in the group of natural numbers. So in cryptography, we are interested, always interested in a finite sets of numbers. Okay. So obviously, what I said, for the rings, ring 5, ring 6, that number cannot be freely chosen if you really want to have the division as, the condition of division fulfilled as well. So if you want to have groups under multiplication, it takes an inverse, and the inverse does not exist for all sets of numbers, as we just discussed. So the question is, where do finite fields actually exist? So we're going to provide a little bit of a rationale, but are not going to be any deeper into this topic area, and just mention the fact without proof. So finite fields only exist if they have a cardinality, meaning a number of elements of p to the m. P to the m. So a little bit so p is a prime number, and m is a positive integer. So what you see here is that if you have m, for instance, being 1, and we're going to see that prime fields are subfields of more general extension fields. So if m is 1, we have a prime number here, okay? A prime number here. So a ring with a prime number, of course, also fulfills the property of invertibility. We discussed that already. So the reason is that the smallest common divisor, the greatest common divisor, excuse me, is 1. Okay, that's a really important condition here. Okay, so examples for finite fields. Well, if we choose p to be 11 and m to be 1, we get Galois field 11. If we choose 3 to the 3, 3 is a prime number, and m is in this case also prime number. It doesn't matter, it's a positive number. We have Galois field 81, or you just leave it like that, okay? So, an especially important finite field is the finite field where p is 2, okay? And m something. So for cryptography, base 2 is an important group of finite fields. Specifically for AES, m is chosen to be 8. Okay, so for our purposes, for AES, Galois field 256 or Galois field 2 to the 8 is what we are going to use in AES. Okay, so it turns out, depending on the choice of m, there are 2 different kinds of finite fields. One is called prime field. It's one that we're not necessarily interested in for AES, but we are going to cover just to make the transition easier to get into extension fields. So in extension fields is really what's being used in AES. So for a choice of n being 1, we get prime fields, okay? So prime fields are basically subfields of extension fields. And extension fields, in this case, n can be anything bigger than 1. So I told you already, for AES, we use Galois field 2 to the 8, okay? So, but in general, for cryptography, Galois fields of 2 to the m are important. So, as I said, first we're going to look into prime fields and see how operations are being done there in computations, just to get warmed up. And then we are going to get into extension fields, which is what we really want to understand for AES. So computation in prime fields. You know, some of these things we have already done, so nothing of that comes as a surprise, as long as we stay in prime fields. So the elements of a prime field are integers from 0 up to p minus 1. And remember, it's important that this is a prime number. P is a prime number, because otherwise the invertibility property would not be fulfilled and we don't have a field. Okay, so you see that we get fields out of rings by limiting, you know, the number of elements to a prime number. So addition, subtraction, multiplication is pretty much what you are already familiar with. So what we do is we do actually a plus b or a minus b or a times b results in an element in the same group. And then we do modulo p reduction, okay? So a plus b is congruent c modulo p. And similarly, a minus b is congruent d modulo p. So now you should convince yourself that addition modulo p is actually XOR, or addition, you know, modulo whatever. So it's XOR. And in XOR, you saw that addition and subtraction is the same thing. All the conditions are fulfilled for groups under addition and multiplication. Okay, so the tricky part is inversion, and given an A element being a member of Galois field P, the inverse of A must satisfy what you already did in the last homework. A times the inverse of A is congruent 1 modulo P. And again, for each A, the inverse must exist, just because you know, we have modulo P here, and the P is a prime, and A and P don't share greatest common divisors other than 1. So the question is, I mean, we can always just try, if we have a certain A, what we can do is we can just multiply them one by one with every other element in the field and see where the result after modulo reduction, of course, is 1. And that way we would find our inverse. So of course, you know, in the long run, with really large numbers, this is not a very good way of finding the inverse of a number, of a member of the prime field. So we're going to see in module 5, we are going to get to know an algorithm which is based on the Euclidean algorithm, which finds the greatest common divisor of two numbers, but it's extended, and the extended Euclidean algorithm actually allows us to find the inverse of a member of a field. Okay, so in other words, this is fulfilled as well. So in prime fields, you know, all four operations are defined. And again, I want to rub it in. It's not different from what we saw with rings, except that we have limited ourselves to the number of elements to be prime. And that trick helped us to get inverses for all of the elements. All of these properties conditions are fulfilled. All right. So let's now look into computations in extension fields. And now remember, for extension fields, m is any number bigger than 1, like 8, okay? So interestingly enough, and kind of scary and surprising and weird, the elements of Galois field 2 to the m are polynomials. They are polynomials, okay? So an element a of x is a member of Galois field 2 to the m, okay? So polynomials that are valid look like that. So the coefficients to the x, these guys here, they are either 0 or 1. Okay, so in other words, the coefficients are members of Galois field 2. So this is a prime field. It's a subfield of Galois field 2 to the m. So you see the connection here, okay? And as such, they're only 0 or 1. So which means that they are also, you know, a less fancy way of saying that they are elements of integer ring 2. Okay, anyhow, it sounds better to call them Galois field 2. All right, so here's an example. For Galois field 2 to the 3, this may be a valid, sorry, in the general case, the polynomials look like that. And basically, you know, to describe the full shot polynomial, all it takes is really the coefficients of a certain element. So all the elements, all the members of Galois field 2 to the 3, remember it's 8 elements, are these. So convince yourself that these polynomials here in this case, they follow a certain order, not that members in a field would have a certain order implied, but it's easier to write them down that way and convince yourself, you know, that you start out with a bit pattern for the different coefficients here with 0, 0, 1, and then you have 0, 0, 0, 0, then you have 0, 0, 1, then you have 0, 1, 0, and you have 0, 1, 1, and then you have 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and you know, 1, 1, 1. So 8 elements, okay? 8 elements. All right. So that said, it should not be difficult to write out all of these elements here. okay? So, but how do we compute in extension fields? So in extension fields, obviously, we have operations on polynomials. So addition and subtraction, that's easy to do. We just do regular polynomial addition and subtraction. So we just add up the elements that have the same order of magnitude. And in the worst case, the coefficients add up to 2, in which case we need to modulo reduce them by 2. Okay, so coefficients are computed in Galois field 2. So in the subfield Galois field 2 with the elements 0 and 1. So let's look into an example. So we have two polynomials, a of x and b of x. A of x is this here and b of x is that. So, and I have them already, I wrote them already such that, same orders of magnitudes are, one above the other. So what you see is when we add up 1 plus 1, we get 2 here. We need to modulo reduce that, and we get 0. So the same is true for the third one here, for x squared. So we have 2x squared, and we modulo reduce that to 0. So for this reason, both this part and this part falls out of the picture, and the only one that is remaining is the x that we had here. So the result of this addition is just x, okay? And because of the way how we did addition, specifically the mod 2 reduction, this is the same as if we would subtract these two polynomials, okay? So, but how do we compute a times b? How do we multiply two polynomials? So what we do is and this is going to be really interesting and mind-blowing and awkward, weird, if you have never heard about it. So we start with regular polynomial multiplication. Like you learned it in school. But the thing here is that if you multiply two polynomials, you may end up with an element that is not part of your field anymore. So we need to do some modulo reduction. And the question is, how do we do modular reduction? Before we did modular reduction with prime numbers like 2, okay, or 5 or 11 or whatever. Here in this case, we do modular reduction using a term that is kind of similar or the equivalent to a prime number as we know them. So in this case, it's an irreducible polynomial. And you know how regular primes are being defined. They cannot be factored, So the only factor in a prime is it's divisible by 1. And irreducible polynomials are similar in that they cannot be factored by two other polynomials. So in other words, irreducible polynomials here in extension fields are kind of the equivalent of prime numbers. So irreducible polynomials, or in different contexts, you will also see the word primitive polynomials. They're not exactly the same, but for our purposes, they behave equally. Irreducible polynomials are basically prime numbers for extension fields. And in extension fields, again, you have polynomials as members. So our prime number that we do modulo reduction by is an irreducible polynomial. So let's look at the same example. We have a of x and b of x, and we multiply these two polynomials, and we get you know, and then we do wherever we hit like here, we get a coefficient that is bigger than 1. That's gonna be modulo 2 reduced. So finally we get the result, okay? So this result, as we can see here, may be just outside of the field. And this would violate, of course, our rule of closeness, our property of closeness. So what do? Well, we modulo reduce, the same thing that we did before, just with regular numbers. So we need to reduce, and we need to reduce by way of an irreducible polynomial. And here comes the surprising thing. So equivalent of a prime, it doesn't factor with any two other polynomials. And the funny part here is that there are several options. There are several irreducible polynomials for a certain field. So you need to choose a certain irreducible polynomial. In other words, your inverse is really depending on the irreducible polynomial that you have been using, okay? So this is kind of creepy, right? Okay, so let's do that example, okay? So we now have this result from the multiplication, and I hereby give you one irreducible polynomial out of several possibilities, and you just have to trust me that this guy cannot be factored by two other polynomials, okay? So what we do is we do polynomial division with this irreducible polynomial. And then, of course, you know, the steps in between, when we have a plus here, when we need to add terms, you know, this is actually a minus normally, but we can write it as a plus because both are equivalent anyways. So dividing our result by the irreducible polynomial gives us a result. And this is obviously within the in our field. So it's contained in our field, okay? So you can follow the steps. It's just regular polynomial division, and the result is a polynomial that is in the field, okay? So this here is our result of A times B mod P. Okay. So in other words, A times B is this here, okay? So we made already that observation a little bit further up. The result of the multiplication actually depends on the irreducible polynomial that you have chosen. And this comes as a surprise that we have several of those. So which means that part of the standard of the AES, we need to define which irreducible polynomial we are using. And actually, the irreducible polynomial for AES is this, okay? So far we talked about multiplication. This is how multiplication is being done, okay? So we do regular polynomial multiplication, and then we divide the result by the corresponding, the one irreducible polynomial that we have chosen, okay? So now inversion. Inversion again is defined through multiplication. So, and in extension fields, inversion is just defined, in an analogous way, how we defined it before. So if we have a polynomial, a member of the extension field, we need to find an inverse, so which is another polynomial, and if we multiply these two, we get 1, and we need to reduce that, of course, by the irreducible polynomial. So you would guess that this is a little bit more involved than just finding, from a small prime field to find, the inverse by just multiplying, reducing, and then seeing whether the result comes out to be 1. And if you want to find, the inverse of A, you run through all the other elements, multiply A by the element, and modulo reduce it. And if the result is 1, then you're lucky and you have the inverse. So here it's modulo. It's polynomial multiplication. So this is more involved. You probably will believe that. So what I said before is true here as well. So the extended Euclidean algorithm can be used, that we are going to get to know in module 6. Wait a minute, did I say in module 5 before up here? I need to check that. Module 5. Huh. Strange. So I don't have the plan before my eyes. Let's just say we are going to cover that later. Okay. So, all right. See later. So for small fields, what we can actually do is we can, Galois fields 2 to the n, we can look up pre-computed tables. Okay. So for instance, the table for Galois field 2 to the 8 is given in the book, and it makes it really easy to look up for any member element of that field, to look up its inverse. So you need to go by this order here, okay? First X and then Y. Let's do an example. Like we want to have the inverse of A of X in hex presentation. This is D1, of course. So we split here. We have 1 here, and we have the D here. So and knowing what your polynomial is in hex, you just go in this table. D is here, 1 is here, and the row and the column cross here. So we have 07, which is the hex representation of the inverse of A. So in other words, if we expand that again, what we get is we get this polynomial. So in order to check that we were right, what we can do is we can multiply this polynomial with this polynomial, and what we do, if we do that, we should get eventually 1 down here, right? And this is actually happening. So what you see, we need to do 2 steps. First, we need to multiply these two polynomials. We get a result. The result is outside of our field. So we need to modulo reduce the result with the AES irreducible polynomial. And what we get is the result is actually 1. Okay. All right, you guys, that's all for this lecture. And in the next lecture, we're going to get to know how these operations are going to be applied in the AES algorithm. Thanks for chiming in and for listening, and see you in the next lecture. Bye.